Okay, I'm wrapping up the section from last lecture, so this is the end of 14.6. And we have a theorem, and the theorem says that the maximum value of the directional derivative is the magnitude of the gradient vector, and that it occurs in the direction of the gradient vector. Let's prove this. So let's start with the directional derivative. And I just want to point out this notation here, this vector x. That just means x could be like x1, x2, all the way up to xn. I drew this vector vertically, but it's the same horizontal or vertically. It just means that it's just a shorthand way of not deciding what place you're in, whether you're in R2, R3, R4. Actually, you need to be in at least R3 in order for the directional derivative to make sense. Okay, so the definition of directional derivative, which we just learned, is the gradient of f times the unit vector in the direction that we want to go in. And that is equal to the directional derivative. Well, we can use our formula. We can look at the magnitude of the directional derivative times the magnitude of the unit vector times cosine theta, where theta is the angle between the gradient vector and the unit vector in the direction that we want to take the derivative in. So we've got the magnitude of the gradient vector times the magnitude of a unit vector, so that would be 1, and then cosine of theta is still cosine of theta. Okay, so now the maximum value of cosine of theta is 1, because cosine goes from -1 to 1. So then the maximum, you can see, is just the magnitude of the gradient vector. Okay, so to prove the other part, the direction, so that's this first part. The second part is that theta is going to be in the same, that u is in the same direction as f. So we're going to look at this. Cosine is maximum. I guess we'll do a unit circle here. Cosine is maximum here at 0. Let me change that to theta equals 0. Therefore, theta equals 0, and the directional derivative, I should say the maximum directional derivative, is in the direction of the gradient vector. Okay, so we have one little example here. Suppose the height of a hill above sea level is given by the function z equals 1000 minus 0.01 x squared minus 0.02 y squared. If you're at the point above 6100, in what direction is the elevation the steepest? And what is the rate of change in elevation at this point? So let's first look at what our hill looks like. which hopefully you can look at it and tell. So if we kind of block out the y, you've got 1,000 minus 0.01x squared. That is a open down parabola in the xz, parallel to the xz plane. And then we have another parabola parallel to the yz plane. And what we get is a paraboloid, and this isn't the best looking paraboloid ever, but maybe I'll throw in some lines and give it. So we have, like, you know, a very generic, very, very generic looking hill. And then what's meant by this at the point 60, 100. So if you go out 60 in the x direction and out 100 in the y direction, let me squeeze back in a little bit. Let's just say we're doing about that. Then on the floor is where this 60, 100 occurs. And then you just come up to whatever the z value is. So if you wanted to find the z value, you could just plug it into there and you would get your elevation. So the direction of the elevation is steepest in the direction of the gradient vector. And the steepness, the change in elevation, is equal to the magnitude of the gradient vector. So we've got the gradient vector is equal to fx comma fy, which in this case, we're taking the partial derivative with respect to x of z. So we're going to get negative 0.02x, and then the partial derivative of our hill with respect to y is going to be negative 0.04y. And then if we evaluate the gradient vector at our point, then when we get, what we get is negative 1.2, negative 4. And that is the direction of maximum steepness. Or the maximum change in elevation. So if we're like here on the hill, or here on top of the hill, and we want to know which way we're going to go, so that is negative 1.2, that's back here, negative 4. So if you notice, it would be like over here somewhere. So something like this. It's exactly what you would expect it to be. So I probably should, it's probably more like this. It's literally going right up the hill because our curve isn't very interesting. And then for answering the second part of the equation, what is the rate of change? That's going to be the magnitude of the gradient vector. So square root of 1.2 squared plus 4 squared. And that should come out to be about 4.2. The units here, let me see if we got units. I don't think there are units, but we can pretend. So maybe this is in feet. And then this would be, is it feet per feet? Not sure. Let me think. I'm just going to put a little question mark on there for now because I don't want to waste time while I'm being recorded. Let me see. So it's going to be the units of both of these rates, right? These are all spatial, so it would be like feet per feet. like 4.2 feet up per foot that you move in that direction. Okay. And that's it for this section. That concludes 14.6. And I'm going to go ahead and leave it there.